Okay, I think it's going. I didn't get a beep to tell me if it was going or not. All right. Now, I wasn't planning on doing this via video, but then doing this live in person, I wasn't sure how well this would work. So, here I am on the video. I'm trying to look at the camera here and not like over on the side of the screen where my face is. I'm trying not to look over there. I'm trying to look at the camera. So, anyway, this is what we had done before we left, right? The four scenarios. I had to get to this one, remember, because we had an incline, we had an angle, and that changes the direction of the forces that we're dealing with. And so I need you to remember that this right here, a surface that is pushing on an object is always going to push perpendicularly to itself. And again, the mathematical term for that is normal. So that's why I drew the little right angle here. This is not a chair. This is not a high back chair. So perpendicular to the surface, normal to the surface. Now, these two forces here, force of the ramp on the block, force of gravity on the block, in this configuration, if I move this tip to tail, which we had talked about in class, if I move this one around here, like that, and then I connect the beginning, the point, the dot, which represents the block, to the tip of the last arrow, which is only the second one because there's only two, then that is what we had called the resultant vector of those two added together. When you add them tip to tail. And so the resultant, again, this is kind of review what we had done before break. The resultant would be this vector right here, which oddly enough is exactly the direction of our acceleration. It is the same inclination as the ramp, because these two forces, the force of gravity pulling down, force of the table up at a perpendicular to the ramp direction, those two forces acting on this block will cause it to slide down the ramp. Or I guess, oh boy, slide down the ramp. I'm trying to, the picture is backward in the thing. I don't know. Anyway, that's the resultant. So I'm going to move this back down here. So it is key for you to get that this vector, force of gravity on block, plus the force of the ramp on the block, those two vectors combined produce this little blue resultant. That is the resultant of those two vectors combined, which produces the acceleration. All right, moving on to number 5. So you were supposed to have done these for today. I think I said all but the last two. So I'm going to do 5 through 10 in one video, and then this is probably going to be way too long anyway. 5 through 10, and then I'll probably stop it and then do another video. So there's 2 separate videos for this rest of this worksheet. Anyway, and I'll try to keep myself in the corner. Static friction prevents sliding. So the static friction. Now, there's 2 kinds of friction, which I think we had mentioned kinetic. Where is it? Yes, object slows due to kinetic friction. Kinetic friction happens when 2 surfaces are moving with respect to each other. The static friction happens between 2 objects or 2 surfaces that are not moving. No movement between the surfaces, then we would call that static or stationary friction. And static friction and kinetic friction are different. So, static friction prevents slide. I would draw then, so I would say my motion map right here. Clearly we have ... because it's not moving anywhere, and so we have no acceleration. For our force diagram, I would say that we have still the gravity force like we had, gravity force on block, and then we will have the normal force, or the force of ramp on block, that is perpendicular to the surface of the ramp. Is that perpendicular? It's close. It might, oh no, it's all connected. Oh, geesh. This is not working out well for me. Oh boy. This is no good. Oh my gosh. What is happening? That's probably similar to what it already was. All right, so if those are the two forces that we just had that in this. Like anytime something's on an incline, you're going to have the gravity force acting vertically. You're going to have the force of the ramp acting off at a 90-degree angle. I should say 90 degrees to the surface of the ramp. But now it says static friction prevents sliding. So do we have an unbalanced force here? Is there an imbalance? Well, no, because we don't have acceleration. No imbalance. The forces have to be in balance. Now here, this force and this force were combining to form this unbalanced force, right? Unbalanced here. So how would this look if it were balanced? That means, what direction do you think friction would be acting on the block? Hopefully you are thinking that the friction force would be like this. Force of friction on block. The friction force is acting parallel to the surface. See, remember, like we said here, friction forces are going to act parallel to the surface. Normal forces are going to act perpendicular to the surfaces. So these would be our three forces here. If I start moving them around, so if I take this one down here, and then I move this one over here, that's close. Notice, the gravity force plus the force of ramp plus the friction force gets us back to the dot. Do you see that? That's balance. Things are balanced when you add up all of your vectors and you get back to the dot. That's balance. So that means the friction force has to be kind of small compared to the other two forces. My force of ramp is probably a little short. That needed to be extended a little bit higher. So instead of being all the way down here, it probably needed to be just a smidge longer. And then when I put this at the tip of there, that's closer. And the friction force is probably even a little bit too long, really. That probably should be more like that, a smidge too long, if you see what I mean by moving that around. So those three forces then, the way they are drawn, at the angles in which they are drawn, that and the lengths that they are drawn, that will produce a balanced force diagram. No acceleration. Hopefully that makes sense. Notice though, the friction force and the force of the ramp, so the normal force and the friction force are at 90s, okay? They have to be right angles to each other because this one's parallel to the ramp, this one is perpendicular to the ramp. Gravity force is just vertical, which it doesn't really look vertical, honestly. That, oh boy. Yeah, something like that. And again, this moves down here. This moves over here. Oh, that even made my friction force have to be even shorter. Yeah, I should, hold on. Let me take a little bit off of that. Oh, not that much. Just a little bit, just a smidge I needed to take off. Maybe that'll work. That's not bad. That's not bad. So I hope you see what I'm doing. Now, again, I have the luxury of doing that here on my board and moving vectors around to get them so that they're the right angle and the right length to make it balanced. You obviously don't have that luxury in your comp books to move things around. But it's important that we know in this case that the only way this can happen is if the force of the ramp on the block, it has to be a little shorter than the gravity force to make this happen. And the friction force is going to be really short compared to the other two. Like this wouldn't extend and be as big as the other two vectors, or it would never get back to the point or the dot in the diagram. Okay, I hope that makes sense. Moving on, number 6. This is taking forever. An object is suspended from the ceiling. Now, I would draw the force diagram. Oh, poop. I would draw the force diagram like, oh no. Oh no. Something happened. Something happened. It froze. Whoa. I would draw the force diagram like this. I would draw it, flip it over horizontally. So now my 0, I'm going to say, is like the floor or something. And then up is the positive direction. And so this thing's just hanging out. It's just kind of hanging out, not going up or down, not sliding even right or left, and it has no acceleration. Now, because there's no acceleration, that means that our force diagram has to be balanced. Just like here, we had no acceleration, had to be balanced. Just like here, we did have acceleration, had to be unbalanced. This one, we have acceleration, has to be unbalanced. So again, I hope you're seeing that that's the pattern here. An object is suspended from the ceiling. Okay, so now we have the object here. What forces are acting on the object? I would say the gravity force. Again, acting vertically, gravity force on block. And what else? Force of, now some people want to put force of ceiling in here. I would not put force of ceiling in here because the ceiling is not touching the object. What's touching the object? There's like a string or something. Force of string on block. Oops, not book, Luke. On block. And those should be, because it's balanced, because it has to be balanced, those should be the same length. Easy enough? Yeah? And next, an object is suspended from the ceiling. All right, another one. 2 cables this time. So again, we still have, let's say the floor is the 0 position. I'm going to say it's not moving. Oops, what am I doing? The acceleration is 0, which means this has to also be balanced. Now we have gravity force like this, force of gravity on, oops, excuse me, on block. All right, it's force of gravity on block like that. And then what? We have 2 cables, and they are at angles. So how do we deal with this? Well, again, each rope, just like this string or rope, whatever, acted as a force of tension. We would call it tension in the cable or in the rope, in the string, pulling up on the block. These 2 are also pulling on the block, but they're pulling at the angle at which they are positioned. So again, ropes can only, and cables and strings and all those things, they can only pull. See, they don't push well. Now, a stick or a rod or a boom or a whatever pole or a, what's another word for all those things? I don't know. So all those things, those can push. Ropes and chains and strings and cables, they don't push well. They pull, and they pull in the direction that they are positioned. So we have a force this way, and we have a force this way. Now here's the question. How long should those arrows be? If this is no acceleration and we need to show balance here, how long should those vectors be? Oh, that angle is that's too shallow. That's too long. How do I know it's too long? You'll see. They might be too short now. And that's force of string on block. And this is another force of string on block. Now, how do we show if these are, that this is going to work in terms of the size of the forces here? Because those aren't as big as the gravity force in my diagram. Those are not as big. So are they the right size? Well, I don't know. I think I might have drawn them a little too short. Oh, are you kidding me right now? There we go. So if I move this one up here, tip to tail, so tip of that one to the tail of this one, and then I move gravity force up here. Oh, I lost my dot. Oh my gosh. I'm trying to get the dot there. Okay, so dot's there. Oh, wrong place. Dot. Oh my goodness gracious. Are you kidding? Oh. Okay. So if that is how this, it's not too bad. It's not horrible. Besides that, my gravity is probably not exactly vertical. That's probably part of the problem. And it might be a touch too long. Maybe I made my, I can't tell if did I even take any off? Not yet. I think what happened was I made my string arrows a little too short. So hopefully you're seeing that when I move that there, they're all tip to tail, and the point of the third vector gets back to the dot. That means I'm balanced. So the only way for this to be balanced is if my string forces, they have to be smaller than the gravity force, so that when I add them tip to tail, they make a vector the same size upward as what the gravity force is downward. Does that make sense? I hope you see that. And object is motionless. Okay, so now we have another motionless object. And again, I suppose I'll draw the force diagram, the motion map sideways again, showing no movement. And we have A is 0. So again, we have balance. We have to have balance because there's no acceleration. And so the forces, what forces do we have? We have the gravity force down, and then that's, I'm struggling with vertical arrows. So gravity force on block. And let's see, we have this string that's pulling to the right. Now, I don't know how long this needs to be. I'll make it kind of short, I guess, because I don't even know. And so that's force of string on block, again, because strings pull, they don't push very well. So force of string on block, and then we have another one that's at this angle here. So that's going to go like this, maybe. No, that's not a good force at all. Something like that. Now, hold on, got to name it. Force of string on block. Now, I suppose since a lot of these have multiple strings, you could be saying force of string 1 on block, force of string 2 on block, whatever. We probably should differentiate between the different strings. But at this point, I don't know that I care. Now, we got to figure out, does this create balance? And when I move them around tip to tail, now, it doesn't matter which one moves where. You can move them anywhere you want, okay? The gravity one can stay put, and you can move the other ones around it. You can move the gravity one and one of the other strings. It doesn't matter what order you move them around in. I get that question a lot, but it doesn't matter. So if I start moving these around, if I go, oh no. No. That goes up here, right there. This goes right. Oh my gosh, that's not bad. That's pretty close. I think this string, I think the horizontal string maybe a little bit long. Take a fuzz off of it. So for this to work, if I go all the way to the tip of that arrow, and then this gravity one goes up, oh, that's nearly perfect. So that right there shows balance. So if I add all three of those force vectors together, the string pulling the one way, the other string pulling this way, gravity pulling down, add them all together, all the vectors together, then they all will get back to the point. Now, what if I move this one down here first, and then move this one over here? So do you see it's still, so I'm still getting back to the dot. It doesn't matter what order I move them around in, as long as I'm moving them tip to tail. You can move them in any order you want. So clearly, the only way for this graphically to work out is if the force of this string, it has to be less than either one of these, or it's not going to work like this is showing. Again, balanced, and another motionless object, and another motionless object. So these are all balanced as you're seeing. They're not accelerating, so there's all balance here. Now I need another motion mat. Oh no. Oh gosh. I thought when it thinks it unlocked it, it unlocked it, and I need to lock. Oops, I need to lock this thing again. Lock in place. Oh my gosh. Okay. Motion mat. Another motion mat with no motion showing and no acceleration as a result. And so again, we still have gravity force acting vertically. Force gravity on block. This is taking forever, I'm sorry. And then we have a normal force. So the surface is pushing this way up on the block, and then we got a string pulling this way to keep it from sliding down. So normal force would be perpendicular to the ramp, so it's going to be like this probably. Oh, that's too much of an angle. Something like that, maybe. And that's force ramp on block. And then we have a string that's going back this way. So now we're looking at a string like that. Or string on block. Now, I want you to take a look here and see. This diagram right here should look really similar to this one. Only instead of friction preventing the sliding, we now have a string preventing the sliding. So do you see that same scenario, but now we have a different agent, and we now have a string instead of the force of friction that's holding the block in place. Now, maybe there is friction too. Maybe there's both acting in the same direction. And if I then move these around, put that up here like this, move this up here like, oh, that's pretty close. That's pretty close. I mean, my dot went with me, so I guess I should leave the gravity one in place. I'll leave the gravity one in place. I'll move this one down, and then I'll move this one over. Oh, dang. Dang. I think my string should be a little bit bigger. String force should be a little bit longer, maybe. That's pretty good. I mean, if I say so myself, that's pretty impressive. So that works right there. And finally, I didn't think we'd ever get there. Number 10. So now we still have, oh gosh, We still have a motion. Oh my gosh. What the? What is happening? Why did I lose my blue? What? How about orange? No, 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 no. Oh, this thing is just not good for me, right? Oh my gosh, now I'm back to blue. Oh my gosh. Is this battery dying? No. Orange. Eraser. Oh my gosh. I apologize for how long this is taking. And again, motionless. 1, 2, 3 dots. And A is 0. And dot. What forces? Well, obviously gravity force. Oh boy, that's pretty bad. Gravity force like so. On block. Now we have the normal force again. It's perpendicular to the surface. And I got to get over here so I can make sure that's about the right. About like, oh gosh. Something like that. Got to make the dot bigger. And force of, what's it called? Ramp on block. And then we have this little short wall here. That wall's pushing this way on the block. And that's going to be parallel to the surface of the ramp. So maybe like that. So force of wall on block. Again, I don't care what you call it. But it has to have a name. You have to have the agent that has a name here. So that's going to put us, now this might not balance as well as some of the other ones did. So if I put this over here like that, then I put this over here like that. Oh, that's pretty close. It's pretty good for, it's good enough for Hoots 4. So those are going to produce balance as well when you move them around. So that's telling you that the wall pushing back this way isn't pushing nearly as hard as what the ramp is pushing perpendicularly to itself. And neither of those are quite as big as what the gravity force is on the block. So proportionally, it kind of gives you an idea that the only way to make this work out graphically here is if the forces are certain sizes. Now, this should look very similar to, maybe, well, I guess it was just a mirror of this one and this one. It's just flipped around. So instead of a string holding the block back, now it's a little short wall holding the block back from sliding down. So there's 5 through 10. If you weren't here before break, then we had these as well. So hopefully you can take a look at those and see what we did there. Now, I didn't write balanced and unbalanced in all of them, but we were talking about them being balanced and unbalanced. And in fact, in 5 through 10, all of them are balanced. So you have to make sure all of them have the forces. When you move them around tip to tail, they all sum to zero, which means all your forces tip to tail are going to get right back to the dot that you started. Okay, I'm going to quit. So this one's going to be done 5 through 10, and then I'll do another video, lucky you, for the rest of it.